Hi, everyone. Thank you for joining the session. I'm Peter Huang, and my colleague Sanas, we are from the streaming platform team at Uber. So today's talk, we will talk about our ongoing effort building unified streaming platform at Uber. This is today's agenda. So we will first go through the overview about the use case at Uber, and also our existing systems like Athena and FAST. After that, we will talk about the motivation of unifying those two systems from the user's perspective and also our infrastructure perspective. After that, given the hybrid cloud is very important, the requirement from our infrastructure side to actually help in the streaming platform on top of it. So Senas will continue to discuss our ideas and the solutions. Then he will come with a conclusion. So let's start from some facts. So Uber's mission is to ignite the opportunity by setting the world in motion. So currently Uber is running in 30 countries, more than 10,000 cities. We will provide services like ride sharing, Uber Eats, Uber Frees. All this business like created like jobs in local business, and also helping the business recovery in the area. So in Uber, we run Flink, Apache Flink for more than 3 years. We accumulate lots of use cases. We can classify them to 4 categories, like real-time decision making, push notification, machine learning use cases, and also OLAP data ingestion. So in the category of real-time decision making, I think the well-known use case is the search pricing. The marketplace team, they use the Flink engine to calculate the supply and demand ratio for last 5 minutes in particular area. So that's when a particular area has like more demand, we can set more higher price, service price, to drive the driver to that particular area, so to make the marketplace more efficient. When you order, if you are the Uber's customer, when you order Uber Eats, so anytime the order status change, you will be notified. So Uber Eats team leverage the Flink engine to read the order status from Kafka and push the information to your app. Also, for drivers, the incentive notification also fall into the category. Uber's machine learning platform team, they leverage real-time streaming processing very much. So because in the real-time model, lots of features need to be calculated in real time, like trip counters for last 1 minute, 5 minutes, 10 minutes. So in this case, usually machine learning engineers, they will launch the streaming processing jobs to calculate these features in window and store into the feature store. When the production request comes, it will join the request info with the features and call to the real-time model sorting service to get the prediction results. Lots of use cases in the fraud detection and the ETA calculation for the orders. The last one is OLAP data ingestion. So as you can see here, this is a use case for the Uber Eats restaurant manager. So with this, our Uber Eats a restaurant manager, they can easily see their real-time earnings by using dashboard. All these things are empowered by Flink at Uber. So all the use cases we talk about are empowered by 2 streaming solutions built by our team. So they are Athena and FAST. So Athena is a self-service SQL-based streaming processing platform. So we have a UI for users to define their streaming SQL, and also define the connectors information, like what's the Kafka topic, what's the Cassandra table name, all this information. So user can easily launch a job in staging within minutes. And also after testing in staging for several hours, there's no issue in the job. The job can be promoted in production. The major advantage is that this is a centralized model. So basically, our team owns all the metadata and also alerts. So once the user put in their job into the production, you don't need to care about the other things. And also, the productivity is very good. So they will have lots of use cases on SNX. The other category is a Flink service. You can get the point from the name. So our major goal is to make some of the use cases can run Flink as like a microservice, so it improve the operation efficiency. For example, the search pricing, their business logic cannot be expressed as a SQL, so they need to use the streaming API to define their business logic. So we provide the highly heavily integrated with the Uber's ecosystem, the libraries for connectors, failover, these things, and also provide a highly reliable deployment solution for them. So even though one HDFS goes down, the job can still launch without data loss. For both of two solutions, we provide a backfill support. So if there's any outage or transient issues, they can leverage backfill solution to replay data and collect data in the result downstream service. And also for machine learning use cases, if they want to use like bootstrap some data from Hive to the downstream data store, they can also leverage our solution. In terms of scale, currently in our platform, we have 2,500 pipelines running in production. Our platform provides 4-9 availability, sub-second latency. For all these pipelines, they are consuming more than 3 trillion messages per day. So all of the information is more about the existing systems and our use cases. So why do we go to the decision of the unification of two platforms? Actually, we think about it from 3 dimensions, basically 3 driving forces. First thing is the operational and the development efficiency. From our experience, we actually support two platforms within 2 sub-teams. When we do the Flink version upgrade, class maintenance, dependency system decommission, all these tasks, we find that we have some duplicated work in both teams. So given we also have lots of user-facing features and work to do, we want to save more energy, the resource for the development purpose. On the other side is customer request. As more and more users onboard into streaming solution, so we find that we have more cooperation opportunity, like with machine learning platform, with like workflow platform. They usually define some template for their business use cases, and also they cannot fall into Athena or FAST. Basically, they provide the DSL templates for us to submit the job. So all these new use cases requires us to provide a unified job management deployment API for them to use. The last and the most important thing is the hybrid cloud requirements. So the company start the initiative to actually leverage cloud resources to achieve cost efficiency and resource elasticity. For our side, we need to provide our solution to tackle the issue. Also, we can see the benefit for us is like some fast-growing streaming applications. They can on-demand get resource in Cloud Zone. After unification, the achievement we can see is that first is the centralized job management. So as I said, the fast job, we don't have the metadata of all the jobs. Every source is owned by the users team. So after unification, we can get all the data. So it's easier for us to build the lineage of each pipelines, create auto alerts, and also apply the global strategies like logging, monitoring, and also the management system there. And also to provide a unified deployment solution. Basically, any feature development for core deployment flow, like add the security support, add the containerization support, can be easily applied to both SQL and API-based streaming applications. In the end, so within the same platform, we can provide unified observability for users to search their job status and also the log information. So when we consider about the requirements and the goes into the design implementation, we see several challenges. The first thing is the heterogeneous system. Basically, the platform needs to handle different type of Flink jobs, like SQL, FAST, and DSL. And also, we can see that the platform needs to support different versions of Flink, at least 2, during the migration and the upgrade. And the last thing is the cluster settings for like security, for like containerization. So we need to be able to handle it in the platform. After unification, we cannot sacrifice the high availability for the critical users. We need to consider about the deployment flow and also dependent systems. Also, as I mentioned, all the core flow use cases like search pricing, they cannot done more than 5 minutes. After that, there will be have like financial losses for the whole company. So we need to make sure our job, all the jobs, during the disaster recovery, we can restart all the job for one cluster within 1 minute. That's our SLA need to provide for the deployment. The last and the most important is the reliability of the ecosystem. Let's first take a look how do we tackle the heterogeneous system problem by defining architecture. As you can see here, there are 3 layers. We have infrastructure layer define different setting of Yarn clusters. We have platform layer define the major functionality in the platform. And the user layer, we have different type of use cases. Let's start from the infrastructure layer. So within Uber, we launched the Flink job in per job cluster for the better resource isolation and the easier resource management. So as you can see here in the leftmost box, this is a Yarn cluster unsecure. We launched a streaming job in this type of cluster. And also we launched the backfill job in the security Yarn to access the secure HDFS information for backfill purpose. For both of these 2 Yarn cluster, our Yarn team installed them into the bare metal machines in the on-prem data center. As I mentioned, there are ongoing efforts to set the on hybrid clouds from infrastructure side. So the Yarn team also, the infra team actually provide a abstraction solution and hidden the underneath hardware locations. So any infra teams, they can install the software like Yarn, HDFS, Cassandra clusters by using the provision solution. And our Yarn team installed containerized Yarn in this setting, and our platform need to deploy the job in a containerized Flink version and to this type of cluster. So we have ongoing effort to secure the streaming Yarn, and also in the end, we need to move to everything onto the provision solution and also interconnect the Yarn. But in the middle, we need to support all 3 types of cluster system to make it work. So to tackle the problem, right? So in the platform layer, we make the deploy highly extendable. Basically, every type of cluster integration module, we put it as a service provider module. So when we initialize a job deployer, so we can use the config to config particular group of deployer to talk to a particular type of Yarn with the protocol. When we try to do some migration or start job from one cluster to another, the job manager can use the job config in the metadata store to actually determine which group of deploy instance to talk to and start a job. In the platform layer, as you can see here, the job manager provide the unified job management API for all bunch of use cases to start a job and manage job, monitor the job. And on the right side, we have watchdog to consistently monitor job healthy to mitigate the transit issues. Job compiler mainly for the job validation, like whether the DSL is correct or the SQL is correct. As I mentioned, Flink version support is a problem here. So as you can see here in the platform, every service is kind of is a Flink version transparent. And there's no Flink dependency in these services, but only the job compiler as Flink support different SQL syntax in their different release. So similar with deployer solution, we have different settings for job compiler part to validate the query from the job manager side. Actually, the platform, we hidden the security and the reliability for our users. We provide schema, data lineage, system observability functionalities, and also we keep on invest on improving the resource estimation for backfill jobs and auto scaling for streaming jobs. From the user side, as you can see here, people, if they want to do some ad hoc tests, they can use our COI to start a job very quickly. And also, there's no impact to fast and SNS existing use cases. Everything is an integration in the backend side. And for the workflow use cases, they define their template in the platform in the UI, and then they can submit the job through JML. There's an interesting part, which is the query proxy. We have the effort to unify the SQL at Uber. So we're talking about translate the Presto SQL into car-side SQL to launch the job, so that people, if they're more familiar with Presto SQL, they can use the Presto SQL to test the SQL and in Presto side get results before launch their job in streaming platform. After this, we need to talk about the high availability of the platform. So the major goal to achieve high availability for those critical use cases, we need full night availability, and also there's no state loss even there's a big outage in the HDFS side. So how do we achieve this? We have two-layer failover torrent. First one is the region side. So in Uber, we have two region data centers. Within each data center, we have a group of machines we call the zone. The zone can be in the prime cloud and also the all cloud. So usually we suggest the customers to set up all active setting. Basically, their pipeline will run in both data centers. It means even one data center goes down, the whole company failover can help to drive the traffic to another data center, make sure there's no big impact from users' perspective. But on our side, we need to further enhance it because we want to make the platform can tolerate zonal failures. What does it mean? It means even a group of machines get impaired, so the platform and the job can still run successfully without the effort of company-wide failover. So how do we achieve that? So we tackle this problem in three layers. First one is storage layer. The second one is dependent system. The third one is the microservice. So first thing, we want to make sure that HDFS there's no data loss. As we know that we cannot specify the policy for the HDFS to distribute the replica files into different zones or locations. So it means when one zone goes down, still there's a possibility that some file get lost or broken. So the solution is we provide a federation on top of two HDFS clusters. It means from client side, we upload the jars configs into both of those HDFS clusters. And also we provide sync services to sync the checkpoint from primary to HDFS to secondary HDFS. So in this way, even the one HDFS goes down, we can still restart the job with the latest checkpoint in secondary HDFS. On the dependent system side, so we definitely use the HA setting for resource manager and node manager. And also we make sure each cluster we have at least 3 resource manager and node manager setting and store in different zone. It means even one zone goes down, we can still rely on the failover to another zone, make active the active IAM and node manager in serve. In the microservice layer, as you can see here, the two major services, job manager service and the job deploy services, we install those like instance in every zone. It means if one zone goes down, we still have like capacity in other zones to handle the request. And also internally, we provide internal fallback logic. In the deployer side, if you detect the failure happens in the HDFS, primary HDFS, they can internally restart the job, retry the job deployments with the setting of secondary HDFS. And also for client side, if it happens, when all the job manager in particular region goes down, it will fail to other region for the continued deployment process. The third thing I want to talk about is the deployment efficiency. Before we deep dive into the details, let's quickly go through the per job cluster deployment process. As if you are using the Flink CLI, right, you have your program code. In the execution environment, it will compile the business logic into the transformation and generate the streaming graph and then the job graph. The Flink Young client will upload the job graph and config files into the HDFS in the storage layer, then launch the application with this like files as local resource for Young. Then once the application mask starts, it will get the job graph, get the resource from resource manager, start the workers. And once the Flink task manager starts, it reaches a slot and also the scheduler will start dispatch the task into different task manager. So from the deployment perspective, the major cost is the client side. There's a heavy business logic to generate job graph. From our profiling for large jobs, usually takes more than 30 seconds. So that's the way we need to think about how can we optimize it. So if you want to extend the COI solution into a service to put into a platform, it's very easy to think about. You probably can use a thread model, right? So for different requests, we use a different thread to start the job graph generation process and also start the application. And it is possible that when you are serving a job with the same job jar, like SQL job, you can use one job template. But in our use case, right, we have different fast jobs. They have different dependencies. and also we have DSL job. We have different jars. It's impossible for us to put everything in the same class path of service. So we have to, in worst case, we have to use a process builder to download a job from remote storage and then start the process. So, but it still doesn't scalable, because if we consider about restart 1,000 job with this kind of scenario, it still cannot meet our SLA. So the solution we propose is to actually push the job graph generation into the operation master. So internally we have our internal implementation, and also we proposed the idea to the Flink 85. Currently it's already released in the Flink 1.11. So the basic idea is, so in the microservice layer, we only responsible for the setting the local resource with the configuration of the job and the metadata of the job in the storage. After the job start from the resource manager layer, then the application master star will read from the configs and also the main class of the Java class, the main class, and the generate job graph internally and submit to the dispatcher, and the further Flink resource manager will get more resource to start execute the job. With this kind of optimization, we can launch more than 1,000 jobs within 1 minute, with minimal resources, like 6 vehicles for each of JMA and the Floyer. And also is highly extendable to horizontal scalable. The last thing is the reliability of the whole ecosystem. So we think about the reliability in 4 layers: the application layer, platform layer, infrastructure layer, and also Flink runtime. In the platform layer, we have black box monitoring, which the service periodically launch the Flink job into our system to different clusters to test the code deployment flow. If any issue happens, we will actually get paged to tackle the issue. And also we have auto alerts for each type of applications, like for the high Kafka lag, job health in the internal failures. If any issue happens, user can actually get paged and tackle the issue. Watchdog service helps our on-call very, very much. We can handle the transparent failures, restart the job. Besides this, we also add the monitoring the cluster. So basically, we will monitoring the resource usage in the task manager process. If there's too much file descriptor or actually CPU cycle usage, we will have paged and also notify the users to prevent any bad application to impact the whole cluster. The last thing is during our operation, we find lots of several things we can improve in the Flink runtime. For example, like when we build the network channel, for the shovel data, so the channel cannot be retried. So when one physical link of a switch have issue, it will cause like a big job initialization always goes down. So we actually applying those patches into Flink that can be shared for the whole community. So currently we already have fast job in production in AUP. So in the coming quarters, we will onboarding new use cases, SNX, and the new platform users. After this, SNS will continue to discuss the hybrid cloud solutions. On you now.
Yeah.
SNS.
Yeah. Yeah. Thank you, Peter. So my name is Sanat, and I'll be talking about some of the design decisions that we had to make for enabling like hybrid cloud platform at Uber. So Peter now has talked about why we have used Athena, why we have developed the Athena unified platform, and also how we have went to a layered architecture to develop that. So one of the main reasons that we initiated this unified platform is the company like Uber is actually want to leverage cloud for better reliability and availability of our platform. So in order for us to run on effectively on cloud, we need to make some design decisions. So when you think of cloud, right? So there are two things that you absolutely need to think about. One is compute, the other is storage. Today in this talk, I'll be primarily focusing on storage, but let's look at the compute abstraction, right? So in the compute, so till now at Uber, the deployments have been done to a particular region, a particular cluster, and the zone. So we as a platform team maintain our cluster with the nodes, add resources, and also maintain the cluster, what goes into the cluster and what goes out of the cluster. So this was actually done by our team for managing the cluster. With cloud coming into picture, we need a way of abstracting out this resource handling and as well as resource allocation in creating a new cluster in a cloud region or in an on-prem region. So for us, the infra provision layer at Uber actually provides this kind of abstraction. So the infra provision layer works with the different cloud vendors as well as on-prem data centers to kind of allocate resources and create a containerized environment. And Yarn is actually uses these hosts to create a containerized environment. And we as a Flink team will use this containerized Yarn cluster to deploy our applications. Now, before going into the storage abstraction and storage, why we need storage, let's look at what our requirements are, like before even considering, right? So at Uber, we run around like 2,500 jobs, and some of these jobs are quite heavy, meaning they are using like 250 plus resources. So in order for all these jobs to run on our platform, the storage that we of our choice should be able to support concurrent uploads and downloads. So we download a lot of job jars and we upload checkpoints, save points. So all these jobs that are running and all these resources that the job is using should be able to download and upload these jars from the storage. So the storage needs to be highly scalable. Also, since they are doing it in a concurrent fashion, the storage needs to do that in a very high throughput manner. Also, there are some jobs in our cluster which are like directly impact the core trip flow. Meaning, if the job is down for more than 1 minute, we have a financial impact. So for these kind of jobs, we need the storage to handle these things in a low latency fashion. So the job should be able to start in less than 1 minute. Now, so considering all this, we actually looked at different storage solutions. So one of the storage solutions we looked at is S3. So primarily we were using HDFS for our storage, but we want to evaluate S3 using S3 completely as our storage, right? So when we did this profiling in our cluster with using S3 for one specific region, we found that S3 upload latency is greater than the on-prem HDFS that we were using. Also, when we use S3 and the jar size is increased, the upload latency increases and the job restart time has increased by 80 seconds. So which will not fall under our SLA. So considering these, we thought S3 might not be a good choice to replace HDFS. But on the other hand, S3 provides fault tolerance and highly availability, whereas HDFS doesn't have this zonal aware deployment. So we initially thought of going in a hybrid solution where we use both S3 and HDFS in different deployment models. So if you look at this diagram, so let's say in region 1 we are using S3 and region 2 we are using HDFS, right? So in this there are specifically two main problems that we found out. So one thing is that when the job is running in using S3 as a storage backend, and the job has to fail over to another region which is using HDFS, there need to be a synchronization service where the checkpoints and jars that are distributed to S3 should be synchronized to HDFS. Also, on top of that, if you think about using two different storage solutions, you need to think about accounting, security, what are the access rights for these different storage solutions. So these all also come into picture, and the development lifecycle or the maintenance becomes a nightmare. The other consideration is that, like, when you use S3, so some of these cloud providers are like do it in a cost basis, meaning it is not so cost efficient with the current Flink model, where each task manager or each job manager will make an individual connection to S3 to download the jars. So when this happens, like we are downloading a huge amount of files from S3, even when the job has a transient failures, when the job has to restart, all this download happens again and again. So with this, it's not so cost efficient also. So that's why we thought of building a storage abstraction, which will take care of all these issues. So so the reason is clear, right? So we have multiple storage solutions where we want to leverage the advantages of different cloud providers as well as on-prem. Like we have HDFS, S3, and Google Cloud, primarily providing storage solutions. And the abstraction will help us to maintain the code as well as increase the developer efficiency. Also, if it helps us in scaling the storage solution, as in if we are adding a new storage provider or new storage solution, it will help us in scaling the application to multiple storage solutions. Also, the other part is the accounting and security. If we have to maintain different security constraints for each of these cloud providers, it becomes a nightmare. So a central system which handles all the accounting and security will help us in using multiple storage solutions. And with this approach, it is also provides a fault tolerance mechanism. So considering all these abstraction, we have built a system called TerraBlob at Uber, which is a centralized managed blob store. So TerraBlob handles the distribution of blobs across different storage providers, meaning HDFS, S3, and it also gives other added benefits, such as it provides a policy-aware storage solution where you create a policy of where the blob needs to go, how many replicas it should have, how it should be served. And the other component that actually helps in this abstraction is Kraken. So Kraken is built at Uber. It is a P2P blob distribution mechanism. Currently, it is serves all the Uber Docker images across our on-prem cluster, and it works very well with hybrid cloud environment. Currently, it serves with 1 million blobs. So TerraBlob and Kraken together will actually provide us the abstraction that we need to have this managed deployment. So let's take a look at an example to get a clear picture of how this works, right? So if you look at this end-to-end flow, so on the top right, there's an admin who will create a storage policy on TerraBlob. So the storage policy could look like, for example, if the blob size is less than 50 MB, store it in S3. If it is greater than 50 MB, then store it in HDFS. And also, it has a replication factor of 2. So primarily store it in HDFS and then asynchronously replica to S3 and other regions and different regions. And also, it can be for this particular job, store in a particular location. So the storage policy is very wide, and it can be highly customized to cater to our needs. So in this case, like the admin creates a storage policy depending on the jobs that are being deployed to that particular cluster. And me as a developer, let's say I'm submitting, in this case, let's take an example of a Flink as a service application where the user is submitting a source code of Flink application. So the code is submitted to the Athena unified platform to the deployer client. So the deployer client will prepare the Uber jar, packaging all the Flink distribution files and as well as the services that are need to interact with TerraBlob, the file systems, into the jar. Now this jar, before getting deployed, it will talk to the job management layer, which actually handles talking to the storage client to the TerraBlob. So the job management layer here will actually communicate with the storage client into TerraBlob to find the location where it needs to upload the jar. And the deployment client uses this the location as well as the tokens needed to talk to the storage client and upload the jar to TerraBlob. Now TerraBlob is smart enough. It sees the blob information metadata, and actually it uses it identifies that this job is let's say we are uploading a core flow critical job, right? So that particular job jar needs to be readily available in case there is a data center failure and the job needs to download. So TerraBlob actually warms up the Kraken cache. So Kraken is like a P2P mechanism, just like totems, right? So Kraken uses this cache to pre-download the jar, so that when the job is actually restarted, it maintains the cache within the host, so that the jar is readily available. There is no latency in going to the network and fetching the jar again. So TerraBlob does this pre-configuration of the jar in the cluster already when the job jar is uploaded. Now the job request is actually going to the job deploy service, where the deploy service says, okay, start the job or start the Flink cluster. So when the request comes to the deploy service to the Flink cluster to start the job, the Kraken agent will get the jar from which is already in the cache and distribute across the cluster to hundreds of nodes. So with this distribution mechanism, we have seen that the latency has drastically reduced, as well as the we were able to start like thousands of jobs with less than 1 minute latencies. So what is the future work, right? So we are actually planning to migrate the Athena X platform into the unified platform, so that we have a centralized job deployment layer, as well as we want to support the backfill use cases, which are currently built on the Kappa Plus architecture, where we want to use both streaming and streaming code to write the batch applications as well. And we want to use TerraBlob as fully integrated with TerraBlob as storage management when we migrate to the cloud. And we want to do an end-to-end deployment with hybrid cloud. So, so today we have discussed about why we went with a unified platform. Discussed about like we have at Uber we manage like 2,500 jobs across multiple clusters, and managing these many jobs deployment with less than 1 minute latency, and deploying 1,000+ jobs when the data center issues happens. This is very critical to Uber. So, and considering hybrid cloud, we wanted to get this platform out. The other thing is the Flip application mode, which has improved our job deployment, which has made our deployment platform very lightweight, and helped us in using the deployment as a microservice to deploy the applications. And also we discussed about the different design strategies that we thought when we're using hybrid cloud. And these are the contributors of the project. They have some of them have left over, and they have contributed quite a lot to this project as well. And yeah, and if you have any questions, we are here to answer. And just that like we are hiring. There's a lot of work involved, and it's pretty interesting time at Uber where we are supporting, where we are working on backfill use cases and other unified platform consideration, hybrid cloud. So it's a good time to join Uber. So if you have any, please reach out to us. You can apply to our website or contact Peter or me. Yep. Thank you.